Good morning, I'm Dinesh Bishokarma and with my teammate Aayush Belekar, we are presenting our project on active to passive voice conversion using LLM parsing. This project combines concepts from compiler design and natural language processing to convert sentences from active voice to passive voice in a structured way. So let's begin with the introduction. Language is a fundamental medium of communication that helps us to express ideas, thoughts, and information in our daily life. However, computers cannot directly understand human language because it is complex and unstructured in nature. So, this is where natural language processing or NLP becomes important as it enables computers to understand, interpret, and process human language. So, in any language, syntax plays a key role in defining how words are arranged to form meaningful sentences. If the structure of a sentence is correct, then its meaning can be properly understood. So, by analyzing this structure, we can not only understand the sentence but also transform it into another form. So in our project, we use the concept to convert active voice sentences into passive voice using a structured and the rule-based approach. Now coming to the problem statement, existing systems from converting acting active voice into passive voice have several limitations. Most of the systems are designed to handle only simple sentence and fail when dealing with complex grammatical structures. Because of this, they often generate incorrect or incomplete outputs. They also face difficulties when processing longer sentences or sentences with a different tense. Another issue is that many systems do not follow a proper structured approach to their accuracy. Therefore, there is a need for a more efficient, structured, and reliable system that can perform accurate sentence conversion. So, this is the main motivation behind our project. Now, let us look at the objective of our project. The objective is to develop a system that can automatically convert active voice and sentence into passive voice. To achieve this, we first analyze the system structure and then apply predefined grammar rules. We use LLM parsing along with context-free grammar, which provides a systematic and inefficient way to process the sentence. These concepts are taken from compiler design and are applied for language processing. We also develop a simple working prototype to demonstrate how the system works in real time. So our aim to is to a- our aim is to make the system accurate, efficient, and easy to understand, especially for basic sentence conversion. Now let us understand context-free grammar or CFG. So it is a formal system that is used to describe the structure of a language using a set of production rules. It consists of a four main components: terminals, non-terminals, a start symbol, and production rules. So the terminals are the actual words in the language, while non-terminals represents grammatical categories like sentence, non-phrase, or verb phrase. The start symbol is the initial point from which the sentence is generated. Production rules defines how non-terminals can be converted into terminals. So CFG helps in generating and sentences and ensure that the input follows the correct grammatical structure before processing. So because of this, CFG is widely used in both compiler design and natural language processing applications. So let us understand parsing. So parsing is the process of analyzing a sentence using grammar rules to check whether it is syntactically correct or it breaks the sentence into smaller components such as subject, verb, and object. So these components helps us to understand the structure of the sentence more clearly. So parsing can be represented using a parse tree, which shows the hierarchical structure of the sentence. So there are two main types of parsing: the top-down parsing and the bottom-up parsing. So top-down parsing starts from the root and breaks it down into the smaller parts, while bottom-up parsing starts from the input and build up the structure. So in our project, we use top-down parsing because it is simpler and works well with LLM grammar, making the system more efficient and easier to implement. Next,
Now I'll continue with the presentation. LL1 parsing is a type of top-down parsing technique used in compiler design. The first L stands for scanning the input from left to right, and the second L stands for producing a leftmost derivation, and one represents the use of a lookahead symbol. This means the parser looks at one input symbol at a time to decide which production rule to apply. Because of this, LL1 parsing does not require backtracking, which makes it faster and more efficient compared to other parsing methods. It is simple to implement and works well with structured grammars. Due to these advantages, LL1 parsing is used in our system to analyze sentence structure efficiently. Next. Now let us understand the working of our proposed system. The system takes an active voice sentence as input from the user. It then analyzes the sentence using context-free grammar, LN1 parsing, and basic part of speech or pause tagging. Pause tagging helps in identifying the role of each word, such as noun, verb, or object. Using this, the system identifies key components like subject, verb, and object. Once these components are identified, the system applies predefined grammar rules to transform the sentence into passive voice. Finally, the system generates and displays the correct passive sentence as output. Next. Now let us look at the algorithm followed by our system. First, the system takes the input sentence from the user. Then it performs pre-processing, where the sentence is tokenized into individual words and unnecessary spaces or symbols are removed. Next, the system identifies important components such as subject, verb, and object. After that, it determines the tense of the sentence based on the verb form. Then the main verb is converted into its third form, also known as V3, and the appropriate helping verb is selected. After that, the positions of subject and object are swapped, and the word by is added before the subject. Finally, the system constructs the passive sentence and displays the result. This step-by-step approach ensures accurate and systematic conversion. Next. Now let us understand the working of our system with an example. Consider the sentence, I write a letter. The system first identifies the subject as I, the verb as write, and the object as a letter. Then it determines the tense of the sentence, which is present simple. Next, the verb write is converted into its third form, which is written. The system then selects the appropriate helping verb, which is. After that, the object, a letter, is moved to the subject position and the subject I is moved to the end of the word by. So the final output becomes a letter is written by me. This example clearly shows how the system converts an active sentence into passive voice step by step. Also, here is a flowchart depicting the same example. Next. Our project demonstrates the LL1 parsing combined with the context-free grammar can effectively convert voice sentences into passive voice. It highlights how concepts from the compiler design can be applied to natural language processing. The system follows a structured rule-based approach, which improves accuracy. It works efficiently for simple sentences and provides correct results in most cases. This shows that the grammar-based parsing techniques can be useful for solving real-world language processing tasks. However, the system also has some limitations. It may not handle complex or compound sentences effectively. It can face difficulties with ambiguous sentence structure and irregular verbs. Currently, the system is mainly focused on basic sentence patterns. In the future, we can improve the system by handling more complex sentence structures and multiple tenses. We also use advanced pause tagging techniques and integrate artificial intelligence and machine learning models to improve accuracy. Additionally, features like speech input and multilingual support can be added. Next. Thank you.